So our next topic here is the conservation momentum. I want you to envision that you're at a hockey game, and one of the, you know, between periods diversions of the hockey game is a game called Chuck-a-Puck. Now we had this when I was in college, and you'd pay like $2 and you get a hockey puck with a number on it, and your goal was to throw your hockey puck after the Zamboni was done after the second period, and you try to get it in center of ice to win a prize. Well, you can imagine they sold around 200 or 300 hockey pucks every night, and you'd chuck it out there. Well, they ran into each other in all sorts of different ways. Well, let's kind of look at how things might work out with example collisions. If you have one, then these hockey pucks are identical. I've just colored them for discussion's sake. So we got a gold puck and a maroon puck. If the gold puck is moving with a certain velocity and the maroon puck is stationary, what could happen? And think back to your bumper car lab that you may have done already. If this one's moving, this one's stationary, it's very likely that the gold puck will stop and the maroon puck will take off with the same velocity. Likely. Remember, these are likely outcomes. If secondly, the gold puck is moving faster and the the red puck is moving slower, it is possible that they will trade velocities. If they're coming at each other with the same speeds, it's feasible that they could bounce away from each other with the same speeds. And this one is hard to tell. Any number of things could happen. The gold puck could continue on slowly while the maroon puck switches the other way. They could, I guess, completely trade, although I think that's unlikely. A number of things could happen. This one's actually very, very hard to predict. The question is, what happens to the momentum of each hockey puck during these events? We'll talk about that. It's being transferred between them. In an isolated system, ladies and gentlemen, that is ignoring outside forces such as friction and whatnot. Momentum is conserved. Ready to write down some notes here. These are a little crazy. Momentum is conserved. Total momentum before an event is equal to total momentum after an event. And when we say an event, we're talking about a car hits a wall, a ball hits your foot, the red car and the blue car bump into each other on the track. It's before the event and after the event. Let's break that down just a little farther here. I color-coded it to represent the two cars from our tracks. Momentum of the red car initial plus momentum of the blue car initial is equal to momentum of the red car final plus momentum of the blue car final. Give you a second to jot that down. Alright, let's break it down one step farther. If you take momentum and make it m times v, mass of the red car times its initial velocity plus mass of the blue car times its initial velocity equals mass of the red car times its final velocity plus mass of the blue car times its final velocity. And this is where paying attention to directions is vitally important. Not just a little important, it's vital. If the red car is going to the left and the blue car is going to the right, you absolutely have to put in a negative sign on one of those two directions. If you don't do that, you will get the wrong answer. It doesn't matter what direction you call left or right, as long as you are consistent. Okay? If you make right positive, you got to make right positive the whole problem. If you make left positive, left has to be positive the whole problem. Or same with north, south, east, west, up, down. Okay? You just have to be consistent with what you're doing, and you will get the right answer. Let's look at a sample together. So Bob here's departing a boat. I want you to think about what's going to happen to the boat. If Bob and the boat are stationary initially, Bob jumps onto the dock. Think in your head, from your experiences or what you've seen on TV or something, what's going to happen to the boat when Bob does that? it's going to scoot backwards. So we're going to show how. So we have this equation here. Let's see, I got a whole bunch of stuff right here. We have to go mass of the person, mass of the boat, initial of the person, initial of the boat, final of the person, final of the boat. So initial velocity of both of them is 0. Guess what? We don't even really need to put their masses multiplied in here. We can. We don't have to, because this whole side of the whole equation, 0, is equal to mass of the person times the final velocity of the person plus mass of the boat times final velocity of the boat. So when we start solving this, we're going to say 0 equals, let's do this, 76, you should be calculating this with me. I mean, you shouldn't be listening to me talk, you should be doing the work. 76 times 0.25, do you have it yet? Do you have it? I got 190. 190 kilogram meters per second. Plus 45 kilograms, be final. Alright. Mathematically, if you want to solve this, looks like you got to subtract 190 over and divide by 45. So subtract 190 over kilogram meters per second. And then we'd have to divide that by 45 kilograms. And 190 divided by 45. 190 divided by 45. I've got my answer. I got 4.22. 4.22 meters per second. But it is going the opposite direction as Bob. Therefore, it's a negative. Notice his direction, we called his direction positive. We have to call the boat's direction negative. It's very, very important that we do that. And then, of course, the boat moves. Showing you the homework on 201, 1 through 3, and you should have some time to work on this in class. Good luck.